day to each and every one of you. So for today's video we will be discussing all about the thermal properties of matter. So in this video again, or in this lecture video, we will be discussing all about the equations of state. We have here equations of state, and also we will be deriving the kinetic energy or the translational kinetic energy, and also we will be deriving the root mean square speed, or we have the VRMS, and also we will prove that the heat capacity at constant volume is equal to 3R/2. Okay, so we will be discussing all of that in this lecture video. Okay, so for the equations of state we have two. Number one, we have the ideal gas law, and we have the van der Waals equation. So we will be discussing this two, and also we will explain when to use each of these equations. Okay, so the ideal gas law or the ideal gas equation and the van der Waals equation, they both describe the behavior of gases under different conditions. Now, while the ideal gas law provides a simple model, the van der Waals equation accounts for real gas interactions. Okay, so let's start first with the ideal gas law. Now, ideal gas law is a fundamental thermodynamic equation that describes the relationship between pressure, volume, temperature, and also the number of moles of an ideal gas. So the formula for the ideal gas law, so we have PV. PV is equal to nRT, or P times V is equal to N times R times T. Now P is the pressure of the gas, V stands for the volume of the gas, we have N is the number of moles of an ideal gas, R is the universal gas constant, which is equal to 8.314 joules per mole times Kelvin. And also we have our T is the absolute temperature, which is in Kelvin. Okay, now this equation assumes that the gas behaves ideally. So meaning, number one, gas molecules occupy no volume, or the gas molecules have no intermolecular forces. I mean, point particles. The gas molecules occupy point particles. Second one is there are no intermolecular forces between the gas particles. And then the third assumption is that the collisions between the gas molecules are perfectly elastic. Okay, so when do we use the ideal gas law? Now, we can use it at high temperatures and low pressures, in which the gas molecules are far apart and the intermolecular forces are negligible. And also, we can also use it in problems where a rough approximation is sufficient. So that is when to use the ideal gas law. Now, let's proceed to the van der Waals equation. So, van der Waals equation is a modification of the ideal gas law that accounts for the finite volume of gas molecules and the intermolecular forces present in real gases. So, di ba, si ideal gas law is for the ideal gas, whereas the van der Waals equation is for real gases. Now, it is expressed, or the van der Waals equation is expressed as, we have here our equation, P plus A over V squared, or V sub M squared, times, we have the difference of V sub M minus B is equal to R times T. So, P stands for the pressure. We have our V sub M is our molar volume. R is our universal gas constant, which is again equal to 8.314 joules per mole times Kelvin, and our T is the temperature. Now, we have here A and B. So, our A stands for the attraction parameter. So, this accounts for intermolecular forces, whereas si B is the repulsion parameter. So again, A is the attraction parameter, B is the repulsion parameter. So si repulsion parameter accounts for the finite molecular volume. Okay, so by the way, there are corrections. Before we proceed, in terms of total volume, so our equation now, or the van der Waals equation now, is equal to P plus AN squared over V squared times, we have the difference of V and N times B, is equal to nRT. So again, this is in terms of the total volume. Okay, so by the way, there are corrections in the van der Waals model or in the van der Waals equation. Now, for the A over V squared, Vm squared term, diba, this accounts for the attractive. So, si A is the attraction parameter. So, this term accounts for the attractive intermolecular forces, reducing the effective pressure. Whereas, the second one, which is the difference of Vm and B, na term, this one, this accounts to the finite molecular size, reducing the available volume. So, those are the corrections in the van der Waals na equation. Now, when do we use this equation? Or when do we use the van der Waals equation? So, we can use it at low temperatures and high pressures, where molecular interactions are significant. We can also use it for real gases rather than the ideal gases. So, for example, noble gases at standard conditions. And we can also use it when working with phase transitions or critical point calculations. Okay. So, this is the comparison between the ideal gas law and the van der Waals equation. So, again, this is the summary of the comparison between the ideal gas and the van der Waals equation. Okay, so to conclude, so we use ideal gas law for low density gases or high temperatures and low pressures, or at high temperatures and low pressures. So, and then we can use the van der Waals equation for dense gases. So, at low temperatures and high pressures, in which the intermolecular forces and the volume effects become important. Okay, now let's proceed to the derivation of the translational kinetic energy equation. So, by the way, the equation for the translational kinetic energy is Ke is equal to 1/2 mv squared, or just K. You can also have K is equal to 1/2 mv squared. So, wherein Ke is the translational kinetic energy, m is the mass of the object, and v is the velocity of the object. Now, how can we derive this equation? So, we can derive using Newton's second law and kinematic equations, or using the work energy theorem or the work energy principles. Okay, so let's derive first the translational kinetic energy using the work energy theorem. Diba? See, work energy theorem states that the net work done on an object is equal to the change in kinetic energy. So we have work is equal to delta Ke, or the change in kinetic energy. Now, if we will define work, if you can still remember the definition of work, work is equal to the integral of force, or F dx. Diba? So, using Newton's second law, if we to express force, so force, diba, is equal to mass times acceleration. So, this is Newton's second law. So, if we will substitute F is equal to ma here in our equation of work, so it becomes, we have work is equal to the integral of ma dx. Okay, so now let's use kinematic relations, or the kinematic equations. So, diba? the acceleration, we can have the acceleration as dv over dt, or the change in velocity over the change in time. So if we will use the chain rule, so using the chain rule, we have A is equal to v dv over dx. Okay, now if we will substitute this one here in our work equation, so we get the chain rule in terms of x na, not in terms of time. Okay, so work now becomes the integral of mv dv over dx times dx. Okay, so obviously ma-cancel out si dx. So what is left is the integral of m times v dv. Okay, so now let's say, or let's evaluate the integral. So evaluating the integral from the initial velocity to final velocity. So let's say our initial is vi. So this is our initial velocity. And vf is our final velocity. Okay, so if we will evaluate the integral from initial to final velocity, so what will happen? Let's continue here. Our work becomes, so pwede na ito mapagawa si m. Okay, so m is constant. M times the integral of from vi to vf, or from initial to final velocity, of v dv. Okay, so we have m times integral of v is v squared over 2. So from vi to vf. Okay, so we have m times vf squared over 2 minus vi squared over 2. Okay, so we can also have it as work is equal to, distributing this one, we have 1/2 m vf squared minus 1/2 m vi squared. Okay, so diba, since work is equal to the change in kinetic energy, or we can also have it as the ke final minus ke initial. So we have 1/2, work is equal to 1/2 m vf squared minus 1/2 m vi squared, or diba, if you can still remember the formula of translational kinetic energy, ke is equal to 1/2 mv squared. So meaning, let's continue it here, work is equal to, we have ke final, so this is our ke final minus ke initial. Okay, so now if the object starts from rest, so meaning vi is equal to 0. So if vi is equal to 0, so substitute here this one. So work is equal to, sorry, let me erase this one. If vi is equal to 0, our ke is just equal to 1/2 m vf squared, or we can have it as ke is equal to 1/2, ma-0 man si initial kinetic energy, so this becomes 0. So ang mabilin is the final kinetic energy. Okay, so the final kinetic energy is just equal to m v squared. Okay, so that is, or we have arrived on the formula for the translational kinetic energy using the work energy theorem. Okay, so we have also an alternative derivation using the Newton's laws or using the Newton's equations. Okay, so using the basic motion equations, we have force is equal to mass times acceleration, and also work is equal to force times distance or displacement. Now, if you can still remember from the kinematic equations, we have 4 kinematic equations. So, if we will use this equation, v squared minus VO squared is equal to 2A times D. Okay, so now, if let's assume that our initial velocity is 0, so if VO is equal to 0, it means, so this one becomes 0. So we have, ang mabili na lang, we have V squared is equal to 2 times A times D. So rearranging the equation to get, or to solve for D. So to solve for D, we will divide both sides with 2A. So D is equal to V squared over 2A. Now, nanatay formula for D. Now, if we will substitute this one, kani si D, in our work equation, si diba, force is MA, and D is, we have V squared over 2A. So, if we will substitute here, we have work, becomes work is equal to force times this displacement. So, our force is M times A, and then our D is V squared over 2A. So, what will happen is, makancel out si A. Okay, so ang mabilin is mv squared over 2. So, mv squared over 2 or 1/2 mv squared, which is, our 1/2 mv squared is the kinetic energy or the translational kinetic energy. So, again, since work is just equal to the change in kinetic energy, diba, change in kinetic energy, but we assume that the initial velocity is 0. So, or KE final minus KE initial. But since our initial velocity is 0, so this one becomes 0. So, work is just equal to the kinetic energy or the final kinetic energy. So, kinetic energy is equal to 1/2 mv squared. So, we have arrived on, or we have derived the translational kinetic energy using the Newton's equations. Okay? So, that's it. So, that is how we would derive translational kinetic energy using the 2 methods. The first one is we have used the work energy theorem, and the second one is we used Newton's equations to derive the translational kinetic energy in a formula. Okay, so we are done with the derivation of the translational kinetic energy. Now, let's proceed to the derivation of the root mean square speed of a gas molecule. Okay, so the root, by the way, the root mean square speed of gas molecules, so it is denoted by VRMS. So it is a measure of the average speed of particles in gases. So it is derived gikan siya sa kinetic theory of gases and relates to temperature and molecular mass. Okay, so now how can we derive the root mean square speed? So we will be using the kinetic theory of gases. So starting with the kinetic theory of gases, according to the kinetic theory, the pressure P of an ideal gas is related to the average kinetic energy of its molecules. So P is equal to 1/3 N over V times M times V squared. So wherein our P is the pressure of the gas, N is the number of molecules, V is the volume of the gas, M is the mass of a one gas molecule, and this one right here is our mean of the squared speeds of the molecules. Okay. Now, so muna ato ang starting na formula from the kinetic theory of gases. Now, from the ideal gas law, if you can still remember what we have discussed a while ago, na PV is equal to N times R times T. And also, the number of molecules N can be expressed as small letter n, which is again the number of molecules times Na is the Avogadro's number. Okay, so let's take note of that because we will be using that later on. Okay, so setting the kinetic energy expression for pressure equal to the ideal gas law. For pressure ni siya ha, di ba si P sa kinetic theory of gases is this one. So we will be using this one. And we will equate that to, so if we will equate this to pressure, we have nRT over V. Okay, so we will be using this one, equate it to this one. Okay, so let's write here. We have 1/3 N over V times M times V squared is equal to nRT over V. Now, if we will rearrange this one to solve for V squared, okay, so we have V squared is equal to, we have 3 nRT divided by M times N. Now, since, di ba, si capital letter N is equal to, we have this one. So, we will be substituting that. So, this becomes 3 nRT over M times N sub A. So, ma-cancel out ang ato ang small letter n. So, ang mabili na lang is we have 3 RT over M times the Avogadro's number, N sub A. So, we have this is V squared. Okay. So, by the way, if we will use the molar mass nga formula, molar mass, let's write it here. So, si molar mass M is equal to M times Na. So, it is the mass of 1 mole of a gas molecule. So, if we will be using that here, so M, capital letter M is equal to M times Na. So, this one now becomes 3 RT over just capital letter M, or the molar mass. Okay, so this is V squared. Okay, so ang next step is to define the root mean square speed. Okay, so diba, si root mean square speed or the VRMS is equal to the square root of the mean square speed. Okay, so let's start from here. So if we will substitute the value, this one, if we will substitute this into the formula for the root mean square speed, so this becomes the square root of 3 RT over M. So, the formula for the root mean square speed is equal to the square root of 3 times R times T divided by M. So, again, this is the root mean square speed. We have our R is the universal gas constant, which is equal to 8.314 joules per mole times Kelvin. We have T is the temperature, which is also in Kelvin, and our M is the molar mass of the gas. Okay, so that is how we would derive the root mean square speed of a gas molecule. So we start from the kinetic theory of gases, and also we've used the ideal gas law, or we equate it to the pressure from the formula of the ideal gas law. So that is how we derive the root mean square speed of a gas molecule. Now, let's have an example problem to calculate the root mean square speed. So we have here for oxygen at 300 Kelvin, so where the molar mass is equal to 0.032 kilograms per mole. So calculate the root mean square speed. Okay, so we have the given of the temperature, we have M, and also since R is a constant value, so given, let's write the given first. So given, we have the temperature, which is 300 Kelvin. We also have the molar mass, which is 0.032 kilogram per mole. And we have our universal gas constant, which is 8.314 joules per mole times Kelvin. Okay, so to solve for the root mean square speed, we have V RMS is equal to, again, it is the square root of 3 times R times T over M. So substituting their values, corresponding values, we have 3 times 8.314 joules per mole times Kelvin times the temperature is 300 kelvins. Okay, divided by M, which is 0.032 kilogram per mole. So, ma-cancel out si 1 over mole of Kelvin, Kelvin. So, we have, ang nabili na unit is joules per kilogram. But take note, joules is, if we will break down joules, so joules is kilogram times what? So, joules, 1 joule is equivalent to, so if we will have it joule from work, so joule is Newton meter, or si Newton is kilogram times meter per second squared times meter. So, we have kilogram times meter squared per second squared. Okay, so we have the square root of, we have 3 times 8.314 times 300 divided by 0.032, and then for the unit, we have kilogram times meter squared per second squared over kilogram. So, ma-cancel out si kilogram, we have meter squared per second squared. So, since square root siya, ang unit nato for the root mean square speed is in terms of meters per second. So, if we will calculate this one, we will arrive with the answer of 483 meters per second, or approximately equal to 483 meters per second. So, the root mean square speed of oxygen at 300 Kelvin is equal to 483 meters per second. Or at room temperature, the oxygen molecules move at an average speed of about 483 meters per second. Okay, so we are done with the derivation of the root mean square speed and also having an example problem calculating the root mean square speed. Now, the next one is to prove that the heat capacity at constant volume is equal to 3R over 2, or 3 over 2 times R. Now, let's define first, or before we will prove that the heat capacity of a gas volume at constant volume is equal to 3R over 2. So, let's define first the heat capacity at constant volume. So, or CV. So, CV is defined as, we have dQ over dt, or the change in the heat over the change in temperature. Now, for an ideal gas, by the way, the internal energy U depends only on temperature. So, it means that at constant volume, the change in the heat is equal to the change in the internal energy. So, if we will substitute this one, instead of dQ, we have CV is equal to du over dt, or the change in the internal energy over the change in temperature. Now, from kinetic theory, or from kinetic theory of gases, the total internal energy, or U, of an ideal monoatomic gas is given by this equation. U is equal to 3 over 2 nRT. So again, N is the number of moles of the gas. R is the universal gas constant, which is equal to 8.314 joules per mole times Kelvin, and our T is the temperature in terms of Kelvin. Now, if we will take the derivative with respect to T or with respect to temperature, kung kaon na to ang derivative ani in terms of or with respect to temperature, so we have, so this one becomes du over dt is equal now to 3 over 2 n times r. Again, common na to ang derivative in terms of temperature with respect to temperature. So, balik ta, di ba, since CV is equal to du over dt, so si CV is equal to 3 over 2 n times r. Now, for 1 mole of gas, when we say 1 mole of gas, it means, so when 1 mole of gas is N is equal to 1. So when N is equal to 1, substitute N is equal to 1 here in our formula. So CV is equal to 3 over 2 R, or CV is equal to 3R over 2. Okay, so we get it. So nakuha na to. So, na-prove na to that the heat capacity at constant volume is equal to 3R over 2 or 3 over 2 times R, or again the universal constant, gas constant, which is equal to 8.314 joules per mole times Kelvin. Okay, so that's it for the heat capacity at constant volume. Okay, so now, how would these 4 topics be related to each other? Okay, so let's have it one by one. So how these topics are related, and they're also to contribution to understanding the gas behavior. So the 4 topics, we have the ideal gas equation, the van der Waals interactions, the translational kinetic energy, and also the root mean square speed. So they are connected through the kinetic theory of gases. So, and also thermodynamics. So together, they help describe and predict the gas behavior under various conditions, from the idealized assumptions to real-world deviations. So number 1, how are they related? Number 1, so let's have the ideal gas law as a starting point. So we have PV is equal to N times R times T. So the ideal gas law provides a basic model for the gas behavior, assuming no intermolecular forces and that gas molecules have no volume. Also, the ideal gas law, as a starting point, it is the first approximation for understanding gases at high temperatures and also low pressures. Now, what is its connection to kinetic theory? So, diba, the kinetic theory of gas molecules directly influences temperature. So, as derived from the equipartition theorem, we have U is equal to 3 over 2 times N times R times T. And also, it is connected through the VRMS, or the root mean square speed formula. So, we have VRMS is equal to the square root of 3 times R times T divided by the molar mass. Okay, number 2, the translational kinetic energy and the gas motion. So we have KE, translational kinetic energy, KE is equal to 1/2 m times V squared. So, si kinetic energy manggod, it explains why gases exert pressure. So the molecules collide with container walls, also transferring momentum. So it also connects temperature to molecular motion. So we have here an equation. So 1/2 m times V squared is equal to 3 over 2 K sub B. So si K sub B here is our Boltzmann constant times T. So T is our temperature. So kani siya nga equation, this bridges the microscopic motion to the macroscopic gas properties. So which means that it is this equation links kinetic energy to temperature. Okay. So number 3, we have the root mean square speed And molecular motion, so again, the formula for the root mean square speed is equal to the square root of 3 times r times t divided by m. So root mean square speed provides a quantitative measure of molecular motion. So it helps explain diffusion, effusion, and temperature dependence of gas properties. So it means that the faster molecules mean higher pressure and temperature, and heavier gases have lower root mean square speeds, affecting diffusion rates. Okay, and then for the van der Waals equation, so this is our van der Waals equation. So while the ideal gas law assumes no intermolecular forces, see van der Waals equation accounts for, number 1, attractive forces, kato si letter A, reducing effective pressure, and number 2, we have the finite molecular volume, which is our letter B, reducing the available space. So what is its connection to the other topics, or for the other 3 topics? So when intermolecular forces are weak man good, the van der Waals equation reduces to the ideal gas law. So also, translational kinetic energy competes with intermolecular forces, which means that higher temperatures reduce the effect of attractions. And also, the root mean square speed is linked to temperature, affecting molecular collisions and also force interactions. Now, together, these concepts create a hierarchical understanding of gas behavior. So, di ba si ideal gas law provides a simple macroscopic model. Si van der Waals equation refined the model for real gases. Si kinetic energy and the root mean square speed explain more on molecular motion, pressure, and temperature. Okay, now let's have an example problem. So we have here, this is a real world problem. Okay, so a weather balloon filled with helium is launched from the ground where the temperature is 300 Kelvin and the pressure is at 1 atm. So the balloon has an initial volume of 2 cubic meters. So as it rises to the upper atmosphere, the pressure drops to 0.20 atm and the temperature decreases to 250 kelvins. So we will solve for the new volume of the balloon at the higher altitude, and also we will calculate the root mean square speed of the helium molecules, both in the lower and also in the higher altitudes. Okay, so let's start first with the new volume. So ang atong pangitaon will be, first is the new volume at higher altitude, and the second one is to calculate for the root mean square speed at lower and higher altitudes. Okay, so the given values, let's write first the given values. Our given values is, we have the initial temperature, T1 is equal to 300 Kelvin. We also have our final temperature, which is 250 Kelvin. Aside from that, we also have an initial pressure of 1 atm, and our final pressure is at 0.20 atm. Okay, and then we have the initial volume at 2 cubic meters. So ang pangitaon nato will be our V2, or our final volume, or the new volume at the higher altitude. Okay, so how can we solve for this one? How can we solve for V2? Okay, so we will use the combined gas law. So since the number of moles in helium remains constant, so we use the combined gas law. So what will happen here is we have, using P1 V1 over T1 is equal to P2 V2 over T2. So again, Since the number of moles of helium remains constant, so the ideal gas law, equating the ideal gas law, initial and final ideal gas law equation will result to this one. Okay, so rearranging this one, if we will rearrange this one to solve for the final volume, V2, so ang goal natin is to get the formula for V2. So what will happen is we multiply both sides with T2 para ma-cancel out si T2. So it becomes P1 V1 T2 over T1 is equal to P2 V2. So we still have P2 here on the other side of the equation. So we will again divide both sides with P2 para ang mabilin na lang sa pika side sa equation will be V2. Okay, so let's continue it here. So we have V2 is equal to P1 V1 T2 over P2 T1. Okay, so we have P1, we have the value of P1, V1, T2, P2, and T1, so we can solve for the new volume or the final volume. Okay, so let's plug in the values. So P1 is 180 m times V1 is 2 cubic meters times our T2 is 250 kelvins divided by P2 is 0.20 and then our T1 is 300 Kelvin. Okay, so let's cancel out some of the units. Ma-cancel out si ATM, ma-cancel out si Kelvin. So obviously, the unit that remains is for the volume is in terms of cubic meters. Okay, so using our calculators to solve for V2, we have 1 times 2 times 250. So this is 500. 500 divided by 0.20 times 300. So our V2 is equal to 8.33 cubic meters. So this is the new volume of the balloon at the higher altitude. Okay, so we are done with the volume or the final volume. Now we proceed to the root mean square speed, both at lower and higher altitudes. Okay, let's have it here on the next slide. So first, diba, the root mean square speed ng formula, we'll write it here para di ta malimot. It's equal to 3 times r times t over m. Okay, so take note na si r is equal to 8.314 joules per mole times Kelvin. Our T1, we have two temperatures. Our T1 is at 300 K. Our T2 is 250 kelvins. And our molar mass, ang molar mass ni helium is 4 times 10 to the power of negative 3 kilogram per mole. So again, this is for helium. Now, let's start with at the lower or at the ground level. Okay. So at ground level, wherein T1 is equal to 300 kelvins. So to solve for the root mean square speed is equal to 3RT1 over m. So we have here square root of 3 times 8.314 joules per mole times Kelvin times T1 is 300 kelvins divided by m, or 4 times 10 to the negative 3 kilograms per mole. So ma-cancel out si mole, Kelvin. So again, we have joules over kilogram, or it is just equal to meter squared per second square. So we have derived this a while ago kung unsay composition ni joules, and then makancel kay kilogram, so ang mabilin will be meter squared per second square. So the root mean square speed at ground level, if you will calculate this one, it is equal or approximately equal to 1,368 meters per second. So this is at ground level or at lower altitude. Now at higher altitude, okay, at higher altitude in which our temperature is at 250 kelvins. So the same formula, root mean square speed is equal to 3r T2 over m. Okay, so we have the square root of 3 times 8.314 joules per mole times Kelvin, then times 250 kelvins divided by, again, 4 times 10 to the power of negative 3 kilogram per mole. Okay, so calculating this one, we have the root mean square speed is equal to, approximately equal to 1,249 meters per second. So this is the root mean square speed at higher altitude. Now, how do we interpret this answer? So it means nga, di ba, balik ta sa first, to get the final volume. So it means that the balloon expands from 2 cubic meters to 8.33 cubic meters as it rises from the lower altitude, or I mean from the lower pressure at higher altitudes. Now, as for the root mean square speed, the root mean square speed of the helium, notice here nga, mas dako ang root mean square speed at the ground level compared to the root mean square speed at higher altitude. So this shows that the molecular motion slows down at lower temperatures. Okay, so this explains why ang mga high altitude na balloons expand as they ascend. And also, the decrease in molecular speed affects diffusion rates, so impacting how gases mix in the atmosphere. So this principle is more on, ay ma-apply siya more on the aerospace engineering, in which the gas behavior must be accounted for in high altitude nga mga vehicle designs. Okay, so ma-apply ni nato siya sa, or this is critical in aerospace engineering. Okay, sa aerospace engineering, they design high altitude vehicles. So this is how we would relate this problem in the real world na relevance. Okay, so I think that's it. So I hope you've learned a lot in our discussion for today, and we'll see you again on our next lecture video discussion. So thank you very much for listening, and we'll see you again on our next video. Bye!